Have we been looking for life in all the wrong places? For decades, our cosmic imagination has been captured by the rusty plains of Mars, the swirling clouds of Venus, the distant promise of exoplanets orbiting faraway stars. We built our search for extraterrestrial biology on a simple terrestrial assumption. You need sunlight, you need a Goldilocks zone, that perfect orbital distance where a planet is not too hot and not too cold, allowing for liquid water to pool on its surface. But what if the universe has other plans? What if one of the most compelling places to search for life isn't a planet at all, but a tiny icy moon, orbiting a gas giant hundreds of millions of miles farther from the sun than we are? I'm talking about Enceladus, one of Saturn's many moons, and it's forcing us to completely rewrite the rulebook on where life could exist. We once thought we understood Enceladus. It's small, only about 310 miles in diameter. You could fit it comfortably within the borders of Arizona. Its surface is one of the most reflective in the solar system, a brilliant, almost pure white, suggesting a landscape covered in pristine ice. Based on its size and its vast distance from the sun, our models predicted it should be a frozen, geologically dead sphere of ice and rock. A simple, inert snowball in space. An object of quiet, cold beauty but not one of dynamic interest. We cataloged it, we measured its orbit, and we largely assumed its story was one of ancient inactivity, a relic from the solar system's formation, now locked in a deep cosmic freeze. But science, in its most glorious moments, loves to shatter our assumptions. The story we told ourselves about this moon was logical. It was based on the physics we knew, and it fit neatly into our understanding of the outer solar system. Small, cold bodies lose their internal heat quickly. Without a significant heat source, there can be no geological activity. No volcanoes, no shifting crust, certainly no liquid water. Enceladus was, for all intents and purposes, considered a closed case. The data sent back by NASA's Cassini spacecraft didn't just add a new chapter to the story of Enceladus. It threw the whole book out the window and demanded we start writing a new one, filled with far more wonder and possibility than we ever dared to imagine. So what did we get so profoundly wrong about this distant, icy world? The answer is everything that truly matters. We misunderstood its energy, its geology, and its potential. We saw a simple snowball and missed the roaring engine hidden beneath its surface. The discoveries made there have prompted a fundamental shift in astrobiology, forcing us to think beyond the comfortable confines of planetary surfaces and sunlit oceans. Enceladus has become a beacon, a shimmering signpost in the dark expanse of the cosmos, pointing us toward a new and revolutionary idea: that the ingredients for life might be hiding in the most unexpected of places, deep beneath the ice of dark, distant moons. The story of Enceladus is a cosmic wake-up call. Let's zoom in on this cosmic celebrity. Enceladus orbits the magnificent ringed planet Saturn. Saturn, a gas giant, almost a mini solar system, over 140 known moons orbiting it. Among this celestial court, Enceladus stands out. It's not the largest, Titan holds that title, but Enceladus more than makes up for size with brilliance. Its surface is covered in fresh, clean ice. It's one of the most reflective objects in the solar system. It bounces back nearly 100% of sunlight. That brightness means constant surface renewal. Something is resurfacing Enceladus, burying craters with fresh ice. That was our first clue. The real showstopper sits at the South Pole. Long, parallel fissures scar the icy landscape. These are the tiger stripes. They aren't just cracks, they're vents. From them, plumes of water vapor and ice erupt continuously. They shoot hundreds of miles into space. Think about that. A tiny moon beyond Jupiter is spraying its internal ocean into space. Those geysers feed Saturn's E-ring. Enceladus is actively building that ring. Where is all this water coming from? Sublimation could explain small puffs of gas, but the volume and persistence pointed to something bigger. Scientists concluded there's a vast liquid ocean beneath the crust, an entire world of water hidden from sight, warmed by internal heat. The bright surface made sense. It's snow from the geysers falling back down. Enceladus isn't an inert snowball anymore. It's dynamic with three key features for life. First, liquid water, a global ocean. Second, a source of energy to keep it liquid and power geysers. Third, complex organic molecules found by Cassini flying through the plumes. Water, energy, organic chemistry. Suddenly, Enceladus is one of the top astrobiology targets. The Cassini mission was a game changer. Launched in 1997, arrived at Saturn in 2004, and spent 13 years revolutionizing our understanding of Saturn. For Enceladus, those observations were transformative. In 2005, A close flyby found a localized warm spot at the South Pole. This was completely unexpected. The rest of the moon was frigid, about -330 degrees Fahrenheit, but the Tiger Stripe region was warmer, a relative hotspot. This was the first concrete evidence Enceladus was generating internal heat right now. Mission planners re-aimed Cassini for closer flybys, targeting the plumes. The spacecraft flew directly through erupting geysers. It was like flying a billion-dollar probe through a cosmic sprinkler. Cassini's mass spectrometer tasted the plume, mostly water vapor, but it wasn't just water. Detected methane, detected carbon dioxide, detected ammonia, detected silica nanoparticles. Those silica grains form only in water at least 194 degrees Fahrenheit, 90 degrees Celsius. This was the smoking gun. It implied hydrothermal vents on Enceladus's seafloor. Think black smokers on Earth's deep ocean floor. On Earth, those vents host ecosystems thriving in darkness, powered by chemical energy. Cassini's final gift, a measurement of the moon's gravity field. By tracking tiny wobbles, scientists could map mass distribution inside Enceladus. The data confirmed Enceladus has a global ocean of liquid water sandwiched between an icy shell and a rocky core. The wobble or libration was too large for a frozen body. The icy crust was decoupled, sloshing on a layer of liquid. The case was closed. Enceladus wasn't a dead snowball. It was a living, breathing ocean world, actively venting its secrets into space. The confirmation of a warm global ocean on Enceladus was a triumph, but it opened a Pandora's box of scientific puzzles. The primary question was simple: how? How could a moon this small, this far from the sun, maintain enough internal heat to keep a global ocean liquid for billions of years? The previously understood heat sources, radioactive decay and leftover formation energy, were simply insufficient. They couldn't power the geysers or stop the ocean from freezing. We had found a phenomenon that broke planetary models. This leads to the biggest puzzle. Could Enceladus support life? Discovery. A liquid water ocean, organic molecules, hydrothermal vents, all three boxes checked. On Earth, life needs water, chemistry, energy. Enceladus appears to have all three. That doesn't mean life is there. Proof is a much higher bar. Well, scientists, forced to think creatively, have honed in on a leading suspect: tidal heating. Enceladus is locked in an orbital dance with Saturn and another moon, Dione. This gravitational relationship isn't perfectly smooth. As Enceladus orbits the massive gas giant, it's constantly being squeezed and stretched by Saturn's immense gravity. Its orbit is slightly elliptical, meaning it moves closer to and farther away from Saturn. This variation causes the tidal forces to flex the moon's interior, creating friction. Just as you can warm your hands by rubbing them together, this constant internal friction generates a significant amount of heat deep within Enceladus. This process of tidal dissipation is, honestly, the most likely candidate for the moon's primary heat engine. The energy generated by this gravitational tug-of-war is focused in its rocky core, heating it from within. This heat then warms the overlying ocean and drives the hydrothermal activity at the sea floor, where hot, mineral-rich water reacts with the rock. This model elegantly explains both the liquid ocean and the silica nanoparticles found in the plumes. It transforms the gravitational energy of the Saturnian system into geochemical energy at the bottom of an alien sea, creating a potentially habitable environment in the process. Furthermore, scientists propose that the core of Enceladus might be porous, like a loosely packed sponge of rock. As tidal forces knead the moon, water could be forced into and out of the cracks and pores within this core. This would dramatically increase the surface area for water-rock interactions and generate even more frictional heat. This porous core model helps explain how such a small body can generate so much power. The heat isn't just coming from simple flexing, but from the massive, turbulent flow of water through a hot, rocky interior, creating a planetary-scale chemical reactor. In addition to tidal heating, chemical reactions themselves could be contributing to the energy budget. The process of serpentinization, where water reacts with certain types of rock to produce heat and molecular hydrogen, could be happening on a massive scale within Enceladus's core. So the solution to the Enceladus puzzle is likely a combination of factors: powerful tidal forces from Saturn, a porous and reactive core, and self-sustaining chemical reactions, all working together to maintain a warm, dynamic, and potentially habitable ocean world. Enceladus is not the only ocean moon in our solar system. Jupiter's moon Europa is another prime candidate, believed to harbor a massive saltwater ocean beneath its icy shell, Ganymede Callisto. So, what makes Enceladus so special? The answer is accessibility. While Europa's ocean is likely much larger, it's trapped beneath an ice shell many miles, perhaps tens of miles, thick. Getting a probe through that much ice to sample the ocean directly is a monumental engineering challenge that we are not yet ready to tackle. It's like trying to drill through a continent of ice here on Earth. Enceladus, on the other hand, is actively serving up samples of its ocean for free. It's literally spraying its internal contents out into space. A spacecraft doesn't need to land, it doesn't need to drill, it doesn't need to melt its way through a thick ice crust, it simply needs to fly through the plumes and collect the material. This makes Enceladus a uniquely accessible target for astrobiology. We can learn about the composition of its ocean, its salinity, its pH, and the complexity of its organic molecules, without ever touching the surface. Thanks to Cassini's plume sampling, we know its ocean contains water, salts, silica, molecular hydrogen, complex carbon-based molecules. This is an astonishing level of detail for a world over 800 million miles away. By contrast, our knowledge of Europa's ocean is much more indirect, based primarily on magnetic field data and surface geology. We have strong evidence that Europa's ocean exists, but we haven't yet been able to taste it the way we have with Enceladus. Because of this, Enceladus presents a clear, near-term path for searching for signs of life. Enceladus offers a shortcut, the low-hanging fruit of ocean world exploration. It shatters the Goldilocks zone paradigm, showing you can have water, organic chemistry, and an energy source in the cold, dark outer solar system. The legacy of the Cassini mission is a call to action. We now know that Enceladus is an ocean world, and we know it is venting that ocean into space. The next logical step is to go back, but this time, we must go with instruments specifically designed to answer the ultimate question. Is there life in that ocean? NASA and other space agencies are already developing mission concepts to do just that. These proposed missions, with names like Enceladus Orbolander and Enceladus Lifefinder, envision sending a new probe back to the Saturnian system. This probe would be equipped with the most advanced life detection instruments ever flown. Imagine a spacecraft orbiting Enceladus, making dozens of low-altitude passes through the plumes. On board, sophisticated mass spectrometers would detect and identify complex organic molecules with far greater precision than Cassini could. They would search for biosignatures, the unmistakable hallmarks of biology, like amino acid handedness or lipids that could form cell membranes. These are the kinds of evidence that would move the needle from potentially habitable to inhabited. Some mission concepts even include a lander, which would analyze freshly fallen snow from the plumes in even greater detail. The first wave of missions like Voyager and Cassini were our scouts. Now, we're preparing to send in the detectives, armed with the tools to solve the case. A mission launched in the 2030s might not reach Enceladus until the 2040s, but the potential payoff is beyond measure. As we plan, studies of extreme Earth environments, hydrothermal vents and subglacial lakes, are crucial for understanding how life might survive on Enceladus. We are, in effect, studying Earth to learn how to explore the cosmos. The quest to understand Enceladus is a mirror, reflecting our own curiosity, our technological ambition, and our unending desire to know our place in the universe. The pale blue dot is our starting point, but the journey to that pale, bright moon of Saturn might just tell us who we really are. Are we alone? What is our place in the universe? This tiny moon offers a tangible, testable opportunity to answer that question within our lifetimes. It teaches us that the universe is more creative and more surprising than we can imagine. It reminds us to question our assumptions and to look for wonder in unexpected places. Finding life on Enceladus would not just be a scientific discovery, it would be a profound moment for all of humanity, forever changing how we see ourselves and our connection to the cosmos. Keep looking up.